This is an overview of my presentation. I'm going to give an introduction to a topic known as magnetic properties mapping using ultra-high field MRI, and then I'll discuss its application for imaging the brain in multiple sclerosis. Then I'll transition from 7T MRI to 3T MRI and from white matter to gray matter, looking at cortical lamination patterns and how they're altered in multiple sclerosis. And then I'll discuss some of my ongoing research at the MNI. So a broad focus of my research is the simultaneous identification of myelin phospholipids and ferritin iron in the brain of MS patients in vivo. Of course, we can do this ex vivo very nicely, and we see that, for instance, in this periventricular white matter lesion, I'll see if I can use my cursor here, there's a simultaneous loss of iron and myelin, and they're co-localized, whereas around the rim of the lesion, we still see evidence of iron. However, these post-mortem stains, although they're nice, we can't, in MS, typically we don't perform brain biopsies. So we'd like to be able to use quantitative MRI to identify these substrates in vivo in a reproducible manner. And one of the techniques I use for this, sorry for the stretching of the brains, it's just the dimensions of the window there. One of the methods we use for this is quantitative magnetic properties mapping, and specifically in the talk I'll discuss three methods: apparent transverse relaxation rate mapping, or R2 star, local magnetic field shift imaging, or LFS, and quantitative magnetic susceptibility imaging. And I'd just like to take a moment to go through what each of these are and how we measure them. So the R2 star measures the rate of signal decay in a gradient echo sequence, and it's influenced by white matter microstructure, including water compartmentalization, magnetic susceptibility, and iron. Values of R2 star are brighter in deoxygenated blood, for instance in the venous vasculature, and darker in regions of white matter lesions where myelin loss is apparent. In this case, darker represents demyelination. And R2 star is measured using a multi-echo gradient echo sequence. Most commonly, there are other techniques, but this is what I'm going to show here. And we can simply represent this sequence. If we look at an image voxel with coherent magnetization prior to the application of an RF pulse, we apply an RF pulse, the spins begin to dephase, and we measure the signal decay in red here at discrete points in time after the RF pulse. We can then fit this exponential decay in the simplest sense to a mono-exponential decay model, and we have voxel-wise maps of R2 star at each point in the brain. And this is a 7T R2 star image from a multiple sclerosis patient. The second technique, which I'll discuss, is the local magnetic field shift. So this represents the induced magnetic field at each point in the brain tissue due to the presence of the strong external magnetic field. You can see here this image actually nicely delineates the basal ganglia structures like the globus pallidus and the putamen, as well as the venous vasculature. But what we get off the scanner in order to derive these images is actually a fairly messy phase image. So we start with this when we're generating our LFS maps, and it has unwanted discontinuities which occur at specific regions in the brain and correspond to jumps of integer multiples of pi in the phase map. So in order to make this information useful in a way where we can perform quantitative MRI, we need to perform two steps. And the first is called phase unwrapping, whereby we do there's a couple ways to do this, but one of them is to perform a 3D spatial search through the image and add integer multiples of pi wherever a discontinuity is located. This leaves us with an unwrapped phase image, which has this sort of slowly varying overlying background field, which is due to contributions from sources outside the brain, like the gradients and inhomogeneities in the main supercon magnet. And we'd like to remove this to extract the underlying structure in the brain, and the way we do this is by modeling these background fields using spherical harmonics, very roughly speaking. These fields obey certain equations, and we can model them because they're slowly varying and have certain physical properties, and then extract the desired underlying tissue structure in the local frequency shift map. However, this map has certain unwanted characteristics, which you can see around the cerebral veins here. There's this, what's known as a brightening artifact around the veins, and this can confound quantitative imaging of the vasculature and of white matter tracts in the vicinity of the vasculature. So in order to remove those unwanted dipole fields, we perform a step known as quantitative susceptibility mapping or quantitative susceptibility inversion. And this is a very active area of research. However, briefly, I'll condense it into modeling this LFS map by a series of magnetic dipoles at each point in the brain. And if we remove the influence of those dipoles, which will have varying magnitudes depending on the tissue structure, we can extract a representation of the underlying magnetic susceptibility chi. And this is typically done by Fourier transforming this image, then zero padding it, and then removing the dipole field, which is represented here in K space, and then coming back to the original image, or the QS image. So with that quick background in mind, I'm now going to move to the application of this technique for 7T imaging of MS. And in particular, in the study that I'll discuss, one of the things we were interested in examining was phospholipid abnormality that extends beyond punctate lesions in MS. So MS imaging, if you get a clinical imaging protocol for MS, what they'll traditionally be looking for is the presence of punctate white matter lesions, which have pronounced proteolipid and phospholipid loss. But there's also been revealed on postmortem histochemical staining quite a large diffuse phospholipid abnormality, which extends beyond the border of these blue lesions and which is not detected on conventional MRI. So this is damage. Could be early damage to white matter tracts, which is not detected on conventional MRI, and we'd like to be able to see it and to quantify it. An associated effect that's been seen in postmortem brains, particularly of more end-stage progressive MS patients, is the accumulation of ferritin iron in the subcortical nuclei of MS patients. So this is called iron overload effect. It leads to the production of free radicals and neuronal cell death. And currently, there's a fairly serious debate about whether this iron overload is a byproduct of traditional MS neuroinflammation and demyelination, or if it's causative of the demyelination, if the production of free radicals plays any role in the T cell and B cell response in MS. So this was sort of the motivation for our work, which we looked at in 2014, a little while back. And for this study, we recruited age and gender matched control subjects, a total of 25 MS patients. Most of these MS patients had fairly early stage RMS or clinically isolated syndrome, which is sort of a pre-MS. And subjects were age matched with an expanded disability status scale of 1.7. So this is the EDSS score is a measurement of clinical disability in MS, which the neurologist will produce. 0 means no disability, 10 means you're dead. So this imaging was all done on a 7 Tesla MRI system, which is really the only one of its kind right now in Canada. As Eve mentioned, there'll be one at the Neuro coming this fall, which will be a whole body system. And one of the challenges with using 7T versus conventional 3T and 1.5T is that if you do your imaging the same way you would at lower fields, you get unwanted brightening artifacts, which are also referred to as dielectric resonances. And these occur because as you go up in magnetic field strength, the wavelength of your transmitted RF field, which you use to excite the signal, is much shorter. So you see this wavelength effect, which is literally the wavelength of the radio frequency field being higher and more spin excitation occurring in the center of the brain. And so in order to account for this inhomogeneity, we took several steps, and one of which was the design of custom radio frequency transmit coils. And the one we used for this study is shown here. It's a plastic former, and then we have 15 channels, 15 copper elements oriented in 2 rows and overlapped relative to one another to limit the electromagnetic coupling between each of them and also capacitively decoupled. So this would be the transmit field coil that we used for our 7T imaging. And each of these coil elements is driven by an independent 1 kilowatt power amplifier, so we can independently control the magnitude and phase of the current running through each of these coils. And by doing that, by manipulating the magnitude and phase, we can improve our imaging somewhat. Some of the intensity biases aren't coming out great on this projector, but there's an improvement just by using the multi-transmit coil. We get rid of some of the center brightening as well as some of the dropouts in the ear canals. So if you want to do imaging in these areas and you're simply using a bird cage coil driven as it would be at 3T, you can't do that at 7T unless you take special steps. But as you can see, even just using the transmit coil produces still some intensity bias, for instance, around the ear canals and at the back of the brain. So this is occurring because different people have different head shapes and different brains will load each of those coils differently. So the RF transmitters will interact with different brain shapes in different ways, and that will lead to different performance of these coils. So we take an additional step in order to try to homogenize the field, and that's known as B1 shimming. And diagrammatically it's shown here. We have each transmitter, which produces its own transmit field distribution, and we can combine them in an intelligent way to try to produce what's a more flat image intensity across the brain. And algorithmically, what this corresponds to is we would acquire images for each individual transmit coil, and then each of these individual images would be acquired with a fairly short TR and a low flip angle for low T1 weighting, and then we would scale them by what are called actual flip angle maps. So flip angle maps acquired using a calibrated measurement of B1 with the coil driven in circularly polarized mode. I won't get into too many details of how this is done, but these calibrated maps can then be fed into a optimization problem with an L2 norm, and we can extract the weights WI, which produce either a more homogeneous field or a B1 power, which is lower. So one of the issues with high field is that you can produce a beautifully homogeneous image, but you may be driving one of these coils at very high power, which is bad because it produces tissue heating. So here you see images taken with a power-efficient B1 shim and images taken with the basic CP shim mode. So by doing this B1 shimming with a multi-transmit coil, we recover quite a bit of the cerebellum and some of the deep brain structures, as well as some of the cortex, which we're interested in MS. And the other piece of the puzzle that's quite necessary for high field imaging is the receive coil. It looks like a Batman helmet here. It consists of 32 individual circular elements oriented roughly equally around the brain, and this coil receives the radio frequency signal from the brain and allows us to produce our images. And this SNR representation on the right side here just shows the gain in SNR which you can achieve by using one of these conformal coil devices. So it's quite pronounced on the cortex and moves down as you move towards the center of the brain. But this SNR translates in the ability to perform quantitative MRI better. So getting back to the study, the imaging protocol we employed used three what I would call conventional imaging sequences. So, well, these two are conventional and this is less so, but a T1 weighted MP range acquisition, which is for structural identification of the cortical gray matter and white matter, a T2 weighted acquisition for identification of hypointense lesions, which are indicative of inflammation, and a multi-echo gradient echo sequence, which is also used for creating magnetic properties maps, such as these. So here, as I talked about in the beginning, the R2 star, LFS, and QS maps, which are paramagnetic maps sensitive to myelin and iron. For each of the patients and controls for this study, the parametric maps of R2 star and QS were registered to an MRI 1 millimeter template space using the 70 MP RAGE image. This is done using nonlinear registration to a template space so that the position of one voxel in the putamen, for instance, in one patient corresponds to the position of a voxel in a control subject. And what you can already appreciate from these images in the template space is that the MS patients have higher iron content, higher R2 star indicative higher iron content in the deep brain structures at the group level, and lower myelin content, for instance, in the optic radiations. The controls values here are darker. In QS, more myelinated fibers appear as darker, so it produces a diamagnetic shift in the main magnetic field, so darker optic radiations means more myelination. But of course, we want to do this in a robust statistical manner at the group level, so what we did is we modeled the QS and R2 signal using a general linear model with an intercept group and age term, and we can produce parametric maps of Z scores where we see either significant iron accumulation in the MS patients at the group level or demyelination, and this was done using a false discovery rate threshold of 0.05 for multiple comparisons correction. And if we do that using our multi-echo gradient echo sequence with the phase data, we can observe regions in the optic radiations in the GNU of the corpus callosum where we see indications of demyelination from the QS maps, from the R2 star maps, and indications of iron accumulation in the globus pallidus and the putamen, as well as in the pulvinar nucleus of the thalamus, which is an area which is known to atrophy early in MS patients. In a subset of RMS patients, this atrophies early. And moving down in the brain, we also see evidence of demyelination, which is predominantly located around the ventricles. This is, if you do any MS study, if you look back through the literature, you'll see a density of white matter lesions around the ventricles. This is believed to be as a result of cerebrospinal fluid infiltrates. And you basically see a congregation of white matter lesions in the vicinity of the ventricles. And here what we're seeing in green is demyelination in regions that didn't have manually identified lesions compared to regions in blue where at least one MS patient had a lesion identified. And the same is true in the superior brain white matter. So a very rough correlation existed between the total volume of demyelinated white matter in EDSS, which is visible using R2 star, and which was visible using QS, but not R2 star. And more generally, we looked at the volume of significantly affected tissue and its correlation with disability, and we found that subcortical gray matter and white matter QS showed mild correlations with EDSS, as well as white matter QS without lesions, so this is normal appearing white matter QS. So another interesting trend, because we had an age regressor in our analysis, was that we observed age-related demyelination and iron accumulation in the brains of MS patients, which was not pathologically related. So our brains will accumulate iron as a function of time. It's been shown in histopathology. It happens as a function of age. But what's not really known as well is how demyelination happens naturally with age in MS patients compared to pathological demyelination. In other words, what is related to lesions. If we break down the results of the subcortical nuclei QS and R2 star a little bit more, we observe that the MS patients have elevated QS values in all of the subcortical nuclei, most noticeably in the globus pallidus, and also elevated iron as evidenced from R2 star, although the globus pallidus didn't show an iron increase for R2 star, which may reflect the sensitivity of these two contrasts for measuring iron. The whole ROI QS and R2 star values also correlated with expanded disability status scale for the globus pallidus and the putamen, with the red X's here corresponding to clinically isolated syndrome patients. So it's a verification that at early stages of potential MS, we see lower values of R2 star corresponding to lower disability. And this was also generally true in the thalamus and the caudate nucleus, which are two other deep brain structures. So to summarize the results of that study, in white matter, we identified damage in lesions as well as in normal appearing white matter in QS as well as in R2 star, and the volume of this damage in QS correlated with EDSS. Well, in subcortical gray matter, very broadly, mean values of QS and R2 star can be used as measures of iron content that may be related to progression of disability. So one of the algorithmic things that I worked on when I was doing this was a pipeline to generate R2 star maps based on the magnitude data and correct them for local magnetic field inhomogeneities, and also to process the phase data from multiple echoes and from multiple receive coils, combine it in an intelligent manner, and then perform the series of steps that I described at the beginning, the phase unwrapping, local frequency shift mapping, and susceptibility inversion. And since we developed this software, we wanted to apply it for areas other than MS, and fortunately at Robarts there was a group, Terry Peters and Maged Goubran, as well as Ali Khan, who were interested in looking at the hippocampal subfields in epilepsy. So in mesiotemporal sclerosis and epilepsy, the hippocampus atrophies, and surgical planning relies on knowledge of the hippocampus and specifically of the hippocampal subfields in order to determine what type of surgical targeting they perform. For instance, in some types of epilepsy, CA1, corneomonas 1 and corneomonas 3 are atrophied, while the other structures are not. And in another type, corneomonas 1 is the only one that is impacted by neuronal loss and atrophy. So the goal of this study was actually to use 7T MRI with these sagittal acquisitions to try to create a manual labeling protocol and automatic identification software for these subfields that a neurologist could use, for instance, to register patient data to a high field atlas. And we created 3D models of the hippocampal subfields based on the R2 star maps and some of the susceptibility weighted data. And we showed that we could do a fairly good job of delineating these subfields. But that's just a sort of an anecdotal example of how high field MRI can be used to create atlases that can be used for neurosurgical planning. And we also did this with the same group for the subcortical structures, including the red nucleus. And the goal of this study was to create really accurate 3D atlases that can be used for deep brain stimulation targeting in Parkinson's. And this is an ongoing study. It's a little bit challenging because these regions are very, very small, so they require high resolution and they require very accurate delineation, which you can't get on a T1 weighted image, and you need to use susceptibility weighted imaging. However, these images can be confounded by fields from the sinus which leak in, so these need to be very accurately modeled in order to do this. So putting that anecdote aside, I'd like to move on to the second half of my talk, which is moving now from the white matter and the subcortical gray matter in MS to the surface of the brain, which is a thin mantle around the cortex, varying in thickness from 1 to 4 millimeters, depending on the anatomical brain region. And in this sort of landmark study in 2005, Alexandra Kutzelnig identified that in progressive MS patients, a large swath of the cortical gray matter is demyelinated in MS, and this was not previously appreciated, certainly not from an MRI standpoint, and that this demyelination appears to spread along multiple sulci and gyri in this sort of wave-like pattern. And this, so what this looks like at a more microscopic level is that if this is the gray matter, white matter boundary, in an SPMS patient, in certain regions of the brain, you can see almost complete phospholipid loss in the gray matter. This is the white matter, so it has more phospholipid, whereas in other regions, you can observe just the expected slow decrease in phospholipid content moving from the white matter to the gray matter. So the real question of this study was, could we use MRI, in this case at 3T, to identify spatial areas of the cortex where this demyelination is occurring and to try to quantify it. And for this purpose, we used a technique known as magnetization transfer imaging, which Eve here has pioneered many great methods for this. We used, in this case, simple magnetization transfer ratio imaging. And basically, what we're trying to do in this technique is that the myelin lipids in the brain are not directly detectable using MRI in general. So we play a trick whereby in our pulse sequence, we can apply a radio frequency saturation to the offset of the macromolecular pool. And if we saturate the magnetization in this pool, it will then transfer to water, and we'll get an image which is a representation of, it's a myelin-weighted image now as a result of the saturation of that macromolecular pool. And we can use this in conjunction with an unsaturated image to create MTR maps, which are relative measures of myelin content in the brain. So this was work done, is published in Neuroimage Clinical, and we looked at surface cortical MTR in a group of MS patients imaged at 2 time points, 25 patients at the first time point, 18 at the second, and 12 at the first and 10 at the second. These are by majority RMS patients with a small group of secondary progressive MS patients, and again, a fairly low EDSS score, although a little bit higher than the previous study I discussed. All imaging was performed on the 3T MRI scanner at the Montreal Neurological Institute using a 32-channel head coil, and we collected standard anatomical brain images, so T1 weighted images for tissue classification and morphometry, T2 weighted and FLAIR images for lesion identification. So lesions in this case are identified automatically using a Bayesian classifier, and they're identified based on these hyperintensities in these two types of images. Using the 1 millimeter isotropic T1 weighted image, we then extracted the layers of the cortical surface. So this image shows the white matter here in the center, and then moving outward, we have the white matter boundary in yellow, as well as what I'll refer to as the inner, mid, and outer cortical boundaries. So under the hypothesis that this subpial demyelination in some cases originates from the cerebrospinal fluid, one current active area of research is to determine whether the outer layers of the peel surface are more demyelinated compared to the inner layers, or whether this is just a gross demyelination that occurs across all layers of the cortex, as I showed in the proteolipid protein staining at the beginning. And so methodologically, we took the quantitative MTR, well, they're not quantitative MTR, the MTR maps, which are relative measures of myelin content. We smoothed them along the cortical surface using a 10 millimeter geodesic diffusion kernel. And then what you get from that is maps of MTR on the cortical surface for MS patients and for normal controls. So one would, these are sort of thresholded in a way where it's a little bit difficult to see, but one would expect from these maps that along the primary motor cortex and superior hippocampal gyrus, you'd see higher MTR values, which we do see, as well as in the area of the cortex above the corpus callosum. So along the inner cortex, we see more yellow values, higher MTR, and as we move outwards towards the peel surface of the brain, we see lower MTR values. And if we just take the whole brain measurements and we look across the 3 layers which we segmented, what we see, which jives with the histology, is reduction in whole brain MTR of the outer and mid cortex, which is not observed along the inner cortex. But to really dig down, of course, we have to spatially parcellate the cortex, and that's what we did using the Desikan-Kilyani Cortical Surface Atlas that's available in the free Surfer package. We parcellated the cortex into 36 individual regions based on anatomical and functional specificity. And we modeled the MTR value, the surface blurred MTR value in each of these regions using a mixed model analysis with interactions between hemisphere and subject as well as group and age. And if we do this ROI analysis, this slide basically compresses a lot of data we got from this ROI analysis. What we interestingly see is there are certain regions of the brain where we do actually see either only outer or outer and mid cortical reductions in MTR, which I'm taking the leap of saying this is demyelination here. And these occur, for instance, in primary motor regions in the anterior cingulate, whereas complete demyelination across the 3 layers is seen in the posterior cingulate, in the precuneus and the cuneus, as well as in the superior hippocampal gyrus. And one of the interesting things about this is that these areas of the brain are involved in default mode connectivity, executive function, and processing speed. So MS patients tend to show quite a large deficit in these. So an intriguing area that different people are looking at is zeroing down on these regions and looking at the whether the reduction in MTR, or your myelin sensitive metric, is causative of cognitive dysfunction, and specifically in the executive function and processing domains. So the other side of the story is there a time-related reduction in MTR? These patients had varying ages and were imaged at multiple time points. So conducting our mixed model analysis, we can look at, as a function of age, are the MS patients in red decreasing in cortical surface MTR along the outer cortex, for instance, more than the inner cortex? And in line with our mean values of MTR, the age-related reduction in MTR in the posterior cingulate, which again is default mode connectivity related, is seen across all layers. I haven't showed the mid layer here, but it's observed there as well. Whereas in some regions, such as the precuneus, we only saw an age-related or progressive, what I'm calling progressive MTR reduction along the outer cortex. And one hypothesis for why this might be the case is that in some regions like this, the MTR value begins to hit a higher degree of demyelination, or a lower value early on in the study, or early on in the lifespan, and then it sort of plateaus. Whereas in other areas, the demyelination is more restricted to the outer layers of the cortex, which is what has been seen on the postmortem histopathology. So we can then go to the highest spatial scale, which we can kind of achieve with this level of image processing, which is the vertex level. So we create surface meshes for all our subjects, and we register to a common template space. And essentially what we're showing here in blue is statistically thresholded regions where the surface MTR is decreased in MS patient group compared to control subjects, and the surface area is actually larger along the outer cortex compared to the mid and inner cortex. Specifically, 27% of the outer cortex has reduced MTR, whereas only about 7% along the inner cortex. And finally, we wanted to try to relate this to clinical disability, the Composite Expanded Disability Status Scale score, which I talked about in my 7T data. And so in this case, what I'm showing is not the vertex-wise difference on a particular layer between MS patients and controls, but the difference between the inner and outer cortical MTR, and how this is correlated with various metrics, including EDSS. And the map shows in hotter colors higher correlations with EDSS for the difference, or the gradient in MTR between patients and controls. And importantly, the gradient in MTR is normalized to the natural gradient we have in MTR values, which exists all over our brains. So finally, I thought it would be relevant to also discuss punctate cortical lesions, because if you're familiar with the ultra-high field MRI literature, a current trend is to just simply identify punctate cortical lesions rather than the diffuse pathology, which I showed in those surface maps. And we had a clinical research radiologist segment cortical lesions in these patients. Interestingly, in many cases, the regions where, I haven't shown it here, but the regions where punctate cortical lesions identifiable based on T2 were located were not co-localized with this type of diffuse pathology. There were some cases, but it's interesting that they don't co-localize. So as expected, in the ROIs for the cortical lesions, the MTR is reduced, and these patients also showed signatures of reduced normal appearing white matter MTR, which sort of harkens back to the first study. There's white matter pathology happening at the same time as gray matter pathology, and an interesting area to look at is how these two are related. If there's tracks connecting to the cortex and there's pathology in a particular region of the cortex, is that a result of white matter fiber degeneration, or is it just occurring initially in the gray matter and then extending inward. So we tried to show that clinically available 3T cortical surface MTR is sensitive to subpial demyelination, and showed that along the outer cortical surface there's more signatures of demyelination in MS compared to control subjects, and the group statistical analysis supports this. So last, I'd like to just talk about some future research in high field MRI at the MNI. As Eve mentioned, there's a 7T human MRI scanner being installed at the MNI in October, which is very exciting. It's kind of pushing the limits, and I encourage any of you who are interested in doing high field imaging to contact me or get involved in this research. So what I've got here is a few areas that my lab works on that we're sort of trying to work on now, and one of them is using one of the features of high field MRI that is unique compared to low field to look at myelin microstructure. So one of the very established areas of quantitative MRI is called myelin water fraction mapping, and Eve's done a lot on this, and others have as well, Bruce Pike, Alex McKay. But one of the challenges with myelin water fraction mapping, if it's done just simply based on the magnitude data, is that we can't separate what's in the interstitial space outside the cells, this should probably say extracellular space rather than interstitial space, from the axonal water and the myelin water, that is the water that's trapped between the myelin bilayers. However, if we use the phase signal, i.e. the magnitude and phase, there's recently been some methods, and one of Eve's students, Eva, has worked on this, to separate these water components using the magnetic resonance frequency shift, or what I referred to as the LFS in the earlier parts of my talk, and we can get distributions of the myelin and axonal interstitial water within a voxel. So I specifically look at this in mouse brains, for instance, trying to compensate for B0 inhomogeneity, which is very important when you're trying to do this high field work, and if we have multi-channel detector arrays at high field, combine the coils in an intelligent manner so we can actually do this properly. And what we'd ultimately like to be able to talk about is, in the extracellular space in MS, there's microglia and macrophages which surround demyelinated lesions, but we know nothing about this based on MRI. We know nothing about what I'll call the extracellular environment. And these types of phase and frequency sensitive techniques at high field MRI have been shown if you model axons within a voxel which have a field shift, different distributions of axons or different packing patterns can produce different histograms for the intracellular, extracellular, and myelin water. And this is very challenging. It requires very high SNR and a large number of echoes, but we're trying to do this to create sort of spatially resolved maps of microstructure. In these cases, this is just a scalar R2 star in susceptibility and myelin, but trying to extract the microscopic features of the myelin histology just based on the MRI data. And another area that I'm interested in working in, but I haven't done a great deal in some time, is chemical exchange imaging. And this is related to oncology. This is a mouse model of glioblastoma where the tumor is shown here in the standard T1 and T2 weighted images. And what this slide is showing is a CEST map of amide proton content, relative amide proton content, shown from 0 to 12% here. And using CEST imaging, what you can try to do is differentiate different tumor microenvironments based on their pH, looking at the amide proton resonance at 3.5 ppm. So I'm interested in doing this, but trying to get that up and running. And finally, as I mentioned, for high field MRI, one of the necessities is the development of hardware. So specifically RF coils. This is a coil which I previously developed for sodium imaging at 7T, which has a nested hydrogen element with a sodium element. So the goal here was to develop a detector which could simultaneously or in an interleaved manner image hydrogen and sodium. And you can also do this for these coils, which are for rat and for mouse brain, respectively. So with that, I'd like to thank my McGill collaborators, as well as the Western group, where I collected a lot of the data, and I'd like to thank you for your attention and welcome any questions.